Okay, so I think we only have a few more lectures left, yeah? This is number 10 of 12. Are things going okay for you guys? You're going to prepare for your exam? No, I see some shaking heads. So our plan for that is we're going to basically release a database of all the exams, tests, assignments. Right? We're going to flood you with practice work. And your exam, 100% of it is extracted from those questions. And so you have the exam, or you will have the exam, except it's going to be distributed amongst hundreds of questions, right? But you cannot complain that we're going to give you something that you have never seen. That is true. You may have not have seen it, but that's due to your own lack of initiative, rather than our lack of providing you the resource. But I really recommend you try to do as many as possible, because practice is, I wouldn't say it's the best way of preparing for your exam. It's really the only way of preparing for your exam. And I want you guys all to do well. So is anyone, no, I don't want to, that's an unfair question to ask. So I convinced Bjorn to change the grading schemes from what we had last year. So the grading scheme this year, the written questions are going to be out of 3, and the grading scheme is going to be, understands the question, right? If you can demonstrate you understand what we're asking, you'll get a point. If you make good progress, you'll get 2 points. And 3 points will be given to those people who get the question correct. Right? So it's more about the process of starting and demonstrating that you sort of, we want to know that you're heading in the right direction. And so don't be overly concerned about making it look perfect. Just try. Right? If you don't know how to solve the question, write down, I don't really know how to solve this, but maybe this is how I would try to do it. Right? And we can give you points allocated on, just by making reasonable progress towards a solution. Certainly don't write nothing. Right? If you leave your question blank, I can't help you. Write something, right? So in the very least, I'll be able to give you a mark. So we've made the grading scheme a lot more flexible for some of the longer questions. So I'm really trying to set it up so you guys can do well. Right? Mainly because I don't want to see you again. But like in a good way, right? Like how they don't want to see you again at the hospital. None of that works for multiple choice, no. But I'll tell you the same thing I told some other people. It's usually none of the above option is there to protect us, right? We haven't designed any question for the answer to be none of the above. That option is there in case we neglect to solve the question properly, and none of the available options are actually the correct answer. So just keep that in mind, right? Normally, if your answer is E, double check, I would say, because that would be against our design. Anyways, what happened here? How many of them are there? A lot. The test is primarily multiple choice questions. And then I think four questions that are like, I don't want to say long answer because they're really short answer. And my section, one of the long answer questions is a question on Green's theorem. Right, so there you go. I've given you half the long answer questions. I think the other one is, you want the other one? I think it's divergence theorem. We're gonna cover that next week. Okay, and then again, everything else I put in the exam is more or less, do you know how to integrate? Can you convert between bounds? And I took off everything that has to do with physics. Right? I'll never ask a question that says calculate work or potential or something like that. This is purely mathematics. So don't worry, don't be overly concerned about memorizing all of those physics terminology. Except maybe there's some stuff today that you'll have to remember. Anyway, so let's talk about curl and divergence. Remember that we're basically studying vector calculus as a mechanism for understanding physics, right? Especially fluid and gas mechanics, right? This is really what the purpose of these vector fields were for. So today we're going to talk about 2 operations that we can define on vector fields, called curl and divergence. Now, I just said that. Well, I'll read it anyways. We define two operations on vector fields that are fundamental to the study of fluid flow and electricity and magnetism. Each operation resembles differentiation, but one produces a vector field, whereas the other produces a scalar field. So a vector field being a function which you give a vector and get a vector back, and a scalar field is a function which you give a vector and get a scalar back. The formal definition of the curl is quite easy to remember. If f is a vector field, then the curl of f is also a vector field given by the Laplace operator cross product the field itself. So do we remember what the Laplace operator is? It's, oh, I have this. Yeah, that is totally correct. Let me play with my toys here. Great. Right, so we have the Laplace operator. I think it's also called del. And for three variables, it's defined to be this. Right? The partial derivatives along each direction. Okay, so what happens if we take the vector field f and we do a cross product with the Laplace operator? This ends up being a fast way of remembering the curl. It's the partial derivative of r. So if f is equal to pqr, pqr being the x component, y component, and z component, the curl of f, in addition to being equal to the Laplace transform, Laplace operator cross product f, if you work that out, it turns into the partial r, partial y, minus the partial derivative of q with respect to z, and so on. So let's work this out. The curl of f, by definition, is equal to the del cross f, which is the determinant of this matrix. Do we remember how to work this out? So the first position here is going to be what we get when we cross out this column in this row. So you have partial r, partial y, minus the off diagonal, which is partial q, partial z. The next one, the j component, is going to be what happens if you strike out this column in this row, which gives us partial p, partial z, minus partial r, partial x. And the last component is what happens when you take the determinant of the matrix left when you cross this column out and this row out. So you can either remember this or you can remember this. I say remember this. It's very easy to work this out from here. Right? But in the end, you'll just be repeatedly filling in this vector. Okay. This is easy. Here's a vector field f. Find the curl. The curl of f is equal to, so remember, this is p, this is q, this is r. Maybe I can do this, actually. Curl of f, delta r, delta y, minus delta q, partial z, partial p, partial z, minus partial r, partial x, partial q, partial x, minus partial p, partial y. Great. I like this whole two-screen thing. Okay, so this is easy, right? You just take the p, q, and r, and you substitute them in for the values here, right? So we had delta r, delta y. So r here is minus y squared, delta y, minus delta q, delta z. So q is this, delta z, and fill out the remainders. Right? Then all that's left to do is to take the partial derivatives. Right? So what's the partial derivative of minus y squared by y? Minus 2y, great. What's partial xyz over partial z? xy, right? So there you go. This is very easy. It's a shame. It would be a shame to get something like this wrong in your exam, right? Because you just have to make sure to take partial derivatives correctly and to employ the curl. Be careful, because we're going to put on your multiple choice answers, we're going to have questions So we're going to have answers where we'll do really dickish things like, here's the answer, and here's the negative version of that answer. Here's the answer, and then here's that same answer backwards, right? They're going to be slight variations, so be sure to choose the correct one, because we're trying to trick you in some sense. We can't make it that easy. Okay, so you'll all be able to do curls, yes? Pretty easy? Actually, let me skip ahead here. Okay, maybe not. I wanted to say pretty easy, and you guys would say yes, that I wanted to give you a hard question, but we'll get to the hard questions soon. Okay, so recall that the zero vector is just a vector comprised of all zeros in any dimension, and that A cross A is 0 for any vector A. Right? If you have two vectors that are the same and you take their cross product, the zero vector is the vector that's perpendicular to both of them, right? Because if you had A and you had A on top of it, what vector is perpendicular to it? Well, there's like an infinite number of vectors that are perpendicular to it, so we choose 0 to identify that entire class. If f is a function of 3 variables with continuous second-order partial derivatives, then the curl of the gradient of f is 0. Now, f is a function, a scalar function. Grad f turns it into a vector field, and curl can take a vector field, right? This is important that these operations are ordered so that these expressions are meaningful. So let's prove that the curl of the gradient of f is 0. Well, the curl of the gradient of f is equal to, by definition, the Laplace operator cross product the gradient of f, which is equal to the determinant of this matrix, right? Down here, instead of having PQR, I have the components of the gradient, delta, partial f, partial x, and so on. So let's just figure out what goes in the first position here, then I'll show you the rest. So the first position is going to be what is left if we strike out this column and this row, which is the second partial derivative of f with respect to yz minus the second partial derivative of y with respect to zy. Right? So if you do that for each of the components, you'll end up getting this. And what's interesting about this? Are we allowed to change the order of differentiation? We are. I think that's called Clairaut's theorem or something like that. But if I change the denominator here, what do you see? What about this one? And this one? Okay, so it is proved. Quande demonstrato. Right? So if we have a vector field which is in fact equal to the gradient of a scalar function, then we know that the curl of that vector field is going to be 0. Vector fields which have this property, that is, their curl is equal to 0, are called conservative vector fields, as opposed to liberal vector fields. You'll learn a little bit more about this in physics, right? For us, it's just enough to know that the terminology is there. When the physicists say that we have a conservative vector field, what they mean is that the vector field has curl 0. Now, if f is conservative, that means the curl of f has to be 0. Right? So, okay, I guess I misspoke. The definition of a conservative vector field is one for which there exists an f so that the grad of f is your vector field. Right? Once your field is conservative, then you are guaranteed that the curl of your vector field is 0. This also means that if the curl of f is not equal to 0, then f is not conservative. This is called the contrapositive. What are we not allowed to conclude? If the curl of f is 0, can I conclude that f is conservative? No. Yeah. No. Well, you said no, which is correct, right? If A implies B, B doesn't imply A. That's a very typical logical fallacy. Right? Do you guys know this? If A implies B, from this you can conclude not B implies not A, but you certainly do not have B implies A. Were you guys taught a little bit of basic logic? You should have been. Right? For example, if it's cloudy, sorry, I I did that backwards. If it's rainy, this means that it's cloudy. But if it's cloudy, does it mean that it's raining? No. If it's not cloudy, does it mean that it's not raining? Yeah. So there you go. There's a little bit of logic. This is actually where I specialized in logic. It's very fun. Prove that this vector field is not conservative. How do we do that? The curl has to be not 0. If it was conservative, then it would be 0. Right? So we have to show that this does not have 0 curl. Well, that's easy. This, in fact, was the vector field for which we found the curl a couple slides ago. And the curl was non-zero, right? So we can conclude that this is not a conservative vector field, right? It's not very interesting, right? This is basically just some another operation that we're defining, right? So mathematically, it's really not that great, but for the physicists, for fluid flow, this is very, very important. Okay, so calculating, I have to go back to the old setup. So calculating curl is really easy, right? Yeah. What's the curl of this? Is this a conservative vector field? Not so easy now, is it? No, but okay, so these questions are very important. These actually took me a little bit of time to work out too. Okay, so let me give you the setup, right? For one, vector fields are typically something that we give in a box in 3D. What I'm saying here is just assume that the z component is 0, right? That the vector field looks the same no matter what level that you're at. Now, we have to ask ourselves a few questions. What are the things that we need to notice here? I think maybe I have this. Cool. I came prepared today. Okay, so if this is our vector field f, in order to determine if it's a conservative vector field, what do we need? We need the curl of f, right? And the curl of f is equal to the Laplace operator cross product, what? I, j, k, d by dx, d by dy, d by dz, p, q, r. Okay. First, what is r? 0. Okay, so. Yeah, I wouldn't recommend copying what I'm doing here because I'm able to do things like delete things at will, but I can post this online afterwards. Okay, so we know that this is 0. Does this change at all as we move z up and down? No. So what is the change of anything with respect to z? Okay, maybe we'll come back to that. So look at the individual vectors that we have here. If I move throughout x, does anything change? Well, look here. Here's one x, and here's another. Are they different? So what is the change of, how are we changing with respect to x? There is no change with respect to x. Okay. Where is there a change? And what happens with y? As y increases, yeah, the vector is pointing smaller. And what do these vectors look like? Well, there's a 0 change in the x, right? These are just upward pointing vectors. There's some q here, which is definitely a function of y, right? Not x. It doesn't depend on x. And the z component is 0. Okay, so let's take this, our information, and stick it into here. This is 0 as well. Okay, so if we work this out, what do we get? Well, in the first component here, we are going to get the derivative of 0 with respect to y, which is 0. And how does q change with respect to z? Q is a function of y only. So the partial derivative with respect to q with z has to be 0. Right? There are no z's in it, so it will disappear. What's the second component? Well, that's the partial derivative of 0 with respect to z, which is 0, minus the partial derivative of the 0 with respect to x. Cool? And what's the last one? Well, it's the partial derivative of q with respect to x minus the partial derivative of 0 with respect to y. And what is this? Q is a function of y only. Therefore, if I take its derivative with respect to x, it becomes 0. Yeah. Get 0, which means this is 0. So, question, is this vector field conservative? Incorrect. No, the blowing this nose thing. It is a conservative vector field because we demonstrated that the curl is 0. Okay? There's one question like this on your homework, which I reluctantly put on there because there's 4 answers and you got 100 tries. And so, before you end up guessing the solution, just give it the old college try, why don't you? But ultimately, yeah, you can just guess. Okay, so let's move on. What is the curl of this? This is a little bit harder. Oops. Okay, so let's work it out in the exact same way, right? If this is f, right, and we know that it has components p, q, 0, right? 0 because that's how it was defined. We just have to do the same sort of jazz, right? So if we're looking for the curl, it's going to be I, j, k, d by dx, d by dy, d by dz, p, q, 0. Okay. So I might as well put a 0 in here, right? Because anything with respect to z is going to be 0. Okay, so let's look at the actual vector field itself then. Let's ask ourselves how it changes with respect to x first. There's one line for x and another line for x. Are they different? No, so there doesn't seem to be a change with respect to x, right? But we can also notice that at each point in this vector field, the answer is going to be something pointing, well, it's not pointing up or down, right? So this is going to look like something like a function of p, which takes x and y, perhaps, 0 elevation, and 0 in the z, right? If you look at one of these vectors, right, this vector is going to be something like minus a, 0, 0. This vector is going to be maybe b, 0, 0. Right? But the point is that there's only ever going to be a non-zero element in the first component. All right. Technology is wonderful. Okay, so really now all we need to do is investigate the nature of pxy. Right, so it seems, what happens as we increase y? So here's one of the y's. Here's another. Yeah, it becomes more positive. So as y is increased, the pxy increases. Okay? What happens if we change this based on x? Did we do x already? Yeah, we proved that there is no change in x. So we can conclude, since there is no change with respect to x, that this p is actually just a function of y. Right? Y is the only thing that's affecting its length. Right? So it's only a function of one thing. Okay, so how can we now take this and determine the curl? Well, this is ijk, partial x, partial y, 0, p, a function of y, 0, 0. Okay, so where are we going to have non-zero terms? Well, the first position is going to be 0 cross 0, 0. The second position is going to be 0 minus 0, 0. And the last position is going to be 0 minus delta p delta y. Okay, so now we have to do one more thing. In order to conclude now, we need to determine if partial p partial y is positive or negative. Which one is it? Right, let's see if we actually understand what derivatives mean. Right? You said exactly the information that we need. As y increases, so does our value. Right? So what does this indicate about the slope, right, of y? It's positive. Right? So delta p delta y is a positive value. Right? So what we really have is 0, 0, something positive. Okay? Something positive negated. I guess that was a dumb way of writing it, but whatever, I'm the boss. Negative. Okay? So the answer to this question is no. First of all, the field is not conservative because it has non-zero curl. And that we can conclude. And the curl is pointing this way, right? Down out of this picture. Okay? So this is really like a treasure hunt, right? When you're doing these types of questions. But it's hard. It's harder than I expected it to be. I was ashamed of myself. Prove that this vector field is conservative, and then find f such that f is equal to delta f. These ones are actually kind of fun in a nerdy way. So in order for this to exist, in order for this f to exist, what do we know what property does f have to have? The curl of f has to equal 0, right, for such an f to exist. So the first sensible thing to do is, well, test if f is in fact conservative. That is, it has 0 curl. The curl of f is equal to this. I hope that's okay, right? We're just filling in the PQR into these positions. If you prefer, you can just take the determinant of that matrix. Once you work out the partial derivatives, right, for example, this one is going to become 6xyz squared. You do that for each component, and look at this, right? We have a bunch of cancellations, so that's 0. So yes, it is conservative, which means that there will exist some f for which we can find the gradient of f equal to f. So let me show you how to do that. Okay, so if you just consider what our goal is, right? Our goal is to find a function f that satisfies these 3 conditions. Right? We know that the partial derivative of f with respect to x is y squared z cubed. We know that the partial derivative of y, do you know where, no, maybe I didn't point this out, right? These are the elements, right? If there is some f so that grad f is equal to f, then these 3 things will be true. Okay? So let's start with what we know about the partial derivative with respect to x, right? We know that f is equal to the integral of partial f partial x dx. Right? If you take f, you take its partial derivative with respect to x, and then you antiderivative with respect to x, you're going to get f back. Right? This means f is equal to the antiderivative of y squared z cubed with respect to x, which just puts that x there, plus a constant. But what's the constant? Right? A constant in this case is anything for which you take the derivative with respect to x and get 0, right? Which means that it's not simply a numerical constant, but a function of y and z. Right? Any function of y and z is going to disappear when you take its derivative with respect to x, right? So we can conclude from this that f is xy squared z cubed plus some function in y and z, right? And just continue. Well, if we take that previous line and we take its derivative with respect to y, right, we know that it should be equal to this. Right? So partial f partial y is going to be 2xy z cubed plus the partial derivative of this function of y and z with respect to y. Right? And we know that this is equal to, well, we know that this must be 0. We know that the partial derivative of f with respect to y is 2xyz cubed, right? So this has to be 0, right? That's the only way it can satisfy that equation, right? So we take that, and now what are we left with? Well, oh, sorry, I misspoke. We know that the partial derivative of g with respect to y is 0. It needs to disappear, which means that at most it's a function in z. Everyone follow that? Do you want me to we'll go over again? Because that's kind of critical. Okay, so from that last line, we can conclude that f now is equal to xy squared z cubed plus some function in z. And we're going to use this last equation here now to move forward, right? Because we know this means that the partial derivative of f with respect to z is going to be 3xy squared z squared plus the derivative of this function of z. Right? And again, we can conclude we need to replace this with something that becomes 0 as you take its derivative with respect to z, and that's a number. Right? So we have that f is 3xy squared plus z squared. Oh, this should be not there. This should just be 3x squared z squared plus k. Right? And you should absolutely check your answer in these situations, right? Because you can very quickly do a derivative. Right? So if you do your gradient afterwards and you find that it hasn't matched, you got to start over. But definitely check your answer. And these are one of these questions that you shouldn't get wrong if you know the mechanics of it, right? If you move and you find that it doesn't answer, you've made a mistake, make mistakes somewhere. We'll do some more at the end of class. I have a bunch more examples. Okay, so physically this curl is important because, again, of gas flow and liquid flow. But specifically it's called curl because it's associated with rotations, right? If you imagine like a big cyclone, or what do you call it here? Typhoon, cyclone, hurricane, one of those weather events. And you want to measure how quickly the wind or gas is rotating around the eye of the storm, for example, right? And that measure is the curl. Right? The longer the curl, the more aggressive the spin. Right? So this is why you'll need this in fluid mechanics, right? So there's a picture. If you have x, y, and z, the curl of f is just a description of how quickly these particles are moving around that pole. If the curl is 0, then there is no rotation. You're just stationary or moving up and down, but you're not rotating about that axis. Right? So you can use this to find whirlpools or eddies in lakes for you physicists. Okay, so we took the Laplace operator and we applied the cross product to it. The natural thing now to do is to now throw the dot product in there and see what we get. Right? If we put in the dot product, now what we have is the divergence of f. Right? So if you have f and it's some vector field, right, that is you give it a vector and you get a vector back, then the divergence of f is given by div f, which is equal to, by definition, the Laplace operator dot product the vector function, right? Provided everything works out. And this is usually our assumption, that we don't have this definition if there are no partial derivatives. Okay, notice that the curl of S was a vector field, right? Curl took a vector field and gives you a vector field back, right? Div takes a vector field and it gives you a scalar back. And so this is important, right? You're going to get a number back, right? Single thing. Here's f. It's a simple vector field, xz, xyz minus y squared. Find div f. Well, this is easy. Div f is equal to the Laplace operator dot product f is equal to the partial derivatives of each of the components along each of these directions, right? So the partial derivative of this with respect to x, the partial derivative plus the partial derivative of this with respect to y, plus the partial derivative of this with respect to z. Okay, let's do a sanity check. What's this? Z this. X Z this. 0. Good. This should be immediate. It should be easy. There's the answer. Right? That's it. So I'm very worried today that I'm going to be short of material because this is basically just mechanics that we're doing. There are some theorems that we can apply here. If f is a vector field whose components have second order partial derivatives, that means each of its components can be differentiated twice in all directions. Then the divergence of the curl of f is 0. Let's prove this. The div of the curl of f, by definition, is equal to the Laplace operator dot product, the Laplace operator cross product f. Right? The brackets here are important, right? There is an order of operations for vector operations. Cross happens before dot. But we'll put brackets just to eliminate this ambiguity totally. Have you ever noticed that stuff on Facebook? Where it's like some simple piece of arithmetic and everyone's fighting over what the answer is because no one knows what badness is? I get tagged in those all the time. just link them to bedness. It's infuriating. Okay. We can just drop in the definition of curl and then take the dot product of that, and we end up with this, right? So this was the first component of the curl, second, third, and then I'm just moving along and summing what happens if we take the partial derivatives in these directions. Okay, so I hope you know that I can take this differential operator and distribute it across that difference. Doing so in each of these cases leaves these derivatives left over. Why did I color them like that? Yes, right, the colored terms cancel, which means that the end result, 0. And really illuminating stuff today, right? These tools that we have to develop for the physicists. Don't tell them it's easy, though, or we'll become unemployed. Okay, show there is no vector field. Oh, do I have an answer for this? Yes. So sometimes we can ask questions like this, right? Is there a vector field G such that F is equal to the curl of G? And we had a question like this before, right? Where we said, well, is F conservative? Is there a scalar function, little f, so that the gradient of F is equal to that? We're asking now a question, is it necessarily the case that every vector field is the curl of something? Right? Do you think we're going to answer this in the positive or negative? You got it. Okay, so let's answer this question. We have that the divergence of F in this case, if we calculate it, is 0. We did that on the last slide, right? Which means, obviously, the divergence is not equal to 0. Towards a contradiction, have you ever seen a statement like this? Okay, so there's a few proof tools we have in our pockets as mathematicians. Induction is one of them. Direct proof is another. This is a very typical way of doing a proof, where you assume something that you know to be false and show that you can derive some sort of contradictory statement from that, right? If you assume something true and show that 2 is equal to 7, the thing that you have assumed is incorrect, right? So towards a contradiction, suppose that F is equal to the curl of G. If F is equal to the curl of G, this means the divergence of F is equal to the divergence of the curl of G, but that's 0 by the previous theorem. Right? We've showed it is always the case that the divergence of the curl of the vector field is 0. Right? So what have I shown? What did I say here? Well, I assume the divergence of F isn't 0, and I prove that the divergence of F is 0. Well, okay, that's bogus, right? Therefore, contradiction, right? Therefore, it is not the case that every vector field has another vector field for which you take the curl of that to get F back. Right? That's not too important. It's just sort of fun to see some of these proofs. Plus, you get to use this really boss lightning symbol if you've never seen it before. That's the symbol for contradiction. I love new symbols because it makes us look so smart. Right, thereby it must be the case that there is no G such that F is equal to the curl of G. Right, so if I ask you a question on your exam, does every vector field F have another vector field for which the curl of that vector field is F? The answer is no. Okay, so divergence also has a physical interpretation. Divergence can be understood in the context of fluid flow. If F is a vector field, which is the velocity of fluids at each point, right? So you have your pipe, you're pushing gas through it, and you're measuring how fast the gas is moving at every point within this pipe, then the divergence of that vector field is the net rate of change of the mass of fluid flowing from XYZ per unit volume, right? So it's telling you, if you have a point, how fast is water moving through this single point, right? And you can answer that question at every piece of the fluid. And that is the divergence of the vector field is a measure of the tendency of the fluid to diverge from X, Y, and Z. If I have a point in like a river, how fast is the water moving away from this point? Right? And that's going to be a scalar quantity, right? Just like the slope was telling us how quickly we were ascending. Right? This is like an analog of that for fluid. Well, hopefully you've been comprehending what I've been saying, but if the divergence of a vector field is 0, then f is said to be incompressible, right? This means that there is no movement at any point of the fluid, right? You can't squish it anymore. Everything is stuck. I hope I'm saying that right. If there's any physicists in here, just feel free to correct me. Okay, despite the fact that curl arguably has a more complicated mechanical equation, I found this question harder to answer. With the divergence of this field. Same setup, right? It's one slice of a vector field that's constant throughout Z. So just assume we're looking at the slice at 0. So you think, and I'm going to play with my toy, boot up FTL here. Okay. Let's play the same game. Right? These scavenger hunts. Right? This is F. We know that it has a P, Q component, and the Z component is 0. We want to take the gradient of F, which is going to be this quantity, delta P, delta X, plus delta Q, delta Y. Y plus, well, delta 0, delta Z. Right? Okay, so what we're really interested is in these values. And since we've already answered a few of these questions before, let's try to do this quickly. The P component here is the X component. And remember that we determined that as we change X, nothing happens. Right? Furthermore, at each of these points, the vector is something like no change in X, right? It's pointing upward. Something, 0. So really, this is going to be 0, Q, which is independent of X, 0. So what do we get down here? Well, we get that the divergence of F is equal to the partial derivative of Q with respect to Y. And what did we determine about that property? What happens to the length of the vector as we increase Y? It decreases, which would indicate that the partial derivative over the slope of this function is negative, which means this is negative, which means divergence is negative. Good job. This one is harder. Let's do the same analysis. This had a red number in it in the book, which means it's hard. Okay, so again, this is our vector field F. We have a P component, we have a Q component, we have a 0 component, and we want to calculate the gradient. And so we need to figure out dP by dx, we need to figure out dq by dy, and then we just have 0. Okay, so again, same analysis. At each of these points, right, this is a vector with, whoa, no, I don't want that. This is a vector that has some x component, which depends on y. It has no height. It's not pointing up, so that component is 0. And we know that the whole z component is 0. Right? So we can calculate the divergence here as being dp, which is a function of y, dx plus d0, dy plus 0, which is 0. Specifically because this is 0. Why? Right? Because it's relevant. We know that we've eliminated the possibility of P relying on X. Right? We know that it's independent of X, which means there's no X in its equation, which means if we take the partial derivative with respect to X, it's a constant, disappears. Okay. So try the same analysis. There's one question like this on your homework. And I don't think there's one on, no, there's definitely not one in your exam. I think. Don't hold me to that. If it is, we only have these 3 examples, so good on you. Okay, Laplace operator, right? So recall that the Laplace's equation, which Bjorn's shown you this, yeah? The German guy who teaches the other section of this course, Bjorn? Okay, well, if he didn't show it to you, I'm showing it to you now, right? Laplace's equation is you take the del operator and you square it and you multiply by f, right? And that gives you the partial second derivatives along every direction of f. Note that we can rewrite this equation as the grad dot product the gradient of f. Right? That is the divergence of a gradient. It's the divergence. Laplace's equation is true if we can take the divergence of a conservative vector field. Right? Those two things are equivalent. Right? So when we're talking about Laplace's equation, we're really interested in conservative vector fields. This delta squared or this del squared is called the Laplace. It's not delta. I don't know why I keep calling it delta. It's del. If I say delta, think del. Dude, it's a del. You guys are too young, maybe. We can also apply the Laplace operator to a vector field in this way, right? Where each of these individual components will become scalars. Right? You guys can check out, if you're a physicist or something else, this is for the mathies in the room. There are two other ways of writing Green's theorem. Right? Remember last week we covered a theorem which allows us to take line integrals, which allowed us to relate the integral about a line to the double integral of the region that is bounded by that line. Right? Using the vector forms, or the new curl and div operators that we just developed, we can write Green's theorem in alternate ways. Specifically, if D is a planar region such that C is the boundary of D, and suppose that F is a vector field which takes a 2D vector and gives you a scalar back, and that all of the hypotheses of Green's theorem holds, which are basically just assertions about the existence of certain partial derivatives, then the closed line integral over C of F dot dr is equal to the double integral over D of the curl of F dot k, where k is the unit z direction. Right? I, j, k are the unit directions along x, y, and z. I'll quickly go over the proof, but don't freak out. If we let f equal pq0, right? So we're taking the 2D vector field and just arbitrarily making it into a 3D vector field by saying the last component is 0. So the curl of f, by our definition, is this, which is, shouldn't there be more than that? Oh, no, because we know that p and q are functions only in x and y, so the partial derivatives with respect to z are going to zero them out. Right? So if you actually go and you expand this determinant, we're only left with the k component, and specifically this k component. And I hope this thing in here looks familiar. Therefore, the curl of f dot k is equal to partial q, partial x, minus partial p, partial y, k dot k. I'm just taking this and multiplying it by another k, which turns it into a scalar. Right? And so we can conclude that the double integral over d, partial q, partial x, minus partial p, partial y dA, is equal to the double integral over the same region, curl of f dot k. Right? It's just, here's another way of writing Green's theorem if you want to relate these line integrals to specifically curls of vector fields. There's another one. The natural question is to ask, well, if we can do it for curls, can we write an equivalent statement for Green's theorem for divergence? The answer is yes. Assume all the hypotheses of Green's theorem again, then the closed line integral over the vector function f, dot product n, the normal, right? So you have to go to RT is the function which is describing this curve C, and n is going to be the normal to this tangent line at t. Then this is equal to the double integral over the region D divergence of f. Right? So this is a way of relating line integrals specifically to the divergence, and this is meaningful for physicists for the purposes of fluid mechanics and gas, which I'm not here to teach you about. Okay, so we're gonna end with, what time is it? Oh God. Okay, so I have prepared exercises which we will do together. It's all handwritten this time, and so to slow me down because I need to waste time. But before, like, people can leave if you want. I'm going to do more exercises, but let's just finish out with this, just to see that we have been paying attention the minimal amount. Okay, so we've given you two operators, a grad and a curl. Which one of the, how many of these are meaningful? That is, are actually meaningful mathematical expressions. And for those which are meaningful, tell me if the result is a scalar or a vector field. Okay, grad of f. What do you get back when you take the grad of f? Because there's not a dot in the middle. This isn't the divergence. This is just the Laplace operator times f, right? Which gives you what? It's this, right? Right? And then when you distribute this f along here, you get this. So you give me a vector, I give you a vector back, which is a vector field. Right? But be careful, there's no dot. Right? That's not the divergence. You even tricked me. I'm like, yeah, that's the answer. Next one. Right? The curl of the gradient of f. Okay, so del f gives you a vector field, which you could give to curl, which gives you back a vector field. Vector field. Okay. Next one. Meaningful? Whoop. Div of f gives you what back? Then if you take the Laplace operator and apply it to a scalar, what do you get? Vector field. Cool. 4. Divergence of f gives you What's the input divergence is asking for? What are we giving? What are we giving it? It's not f, which is a scalar field. Can you take the divergence of a scalar field? So the answer is meaningless, like my life. Next one. What is the divergence of a vector field? Gives you back. Okay. So, meaningless. Grad f gives you what? Curl of a vector field gives you what? Div of a vector field gives you. Okay. Your homework has, okay, so in the notes, there's 2 columns of this. This is the right column. On your homework, you'll be asked to do the right column, right? We did the answers to that, as well as the left column. So I've given you half of a homework question. Okay, so let's move on. I have more questions. These are taken right from your Stuart. Whoever wants to leave, you have my blessings. I won't get offended. This paper okay? Like, there's different options here. I can, we can switch to this if you want. No? How about that? Actually, maybe black would be better. What do you guys reckon? Back to the... Okay. To this. Cool. All right, so let's do some work. Oh boy. All right. This is much nicer. It's a much more natural writing angle. Okay, so this is question from 16.5. Oh, this is version 8, Stuart. So 16.5, question 1. Find the div and curl of f. Okay. F is PQR, which is xy squared, z squared, x squared y, z squared, x squared, y squared, z. Cool. So we want the div of f. Okay, so let's do this. It's the partial derivative of p with respect to x, which is what? Y squared, z squared, plus the partial derivative of q with respect to y, which is x squared, z squared, plus the partial derivative of r with respect to z, which is x squared, y squared. Right, easy peasy. The curl of f, that's equal to the derivative, the determinant of this vector field, or of this matrix. So partial x, partial y, partial z, and in here, x, y squared, z squared, x squared, y, z squared, x squared, y squared, z. Then we just have to work out each of the components. First component is what happens when I eliminate, if I eliminate this row and this column. We take the determinant of what's left, which is what? It is partial this, partial y, which is 2x squared y z minus this cross diagonal, 2x squared y z. The next component is what is left when we cross out this column, this row and this column, which is partial this with respect to z, which is 2xy squared z, minus that diagonal. So it's partial x squared y squared z with x, which is 2x y squared z, which is what? 0, 0, 0, which means f is conservative. Cool. All right, so these div and curl questions are pretty easy. At least the mechanical questions are pretty easy. The theoretical questions can get kind of difficult. Let's do another one. This is 16.5, question 6. Our vector field here is ln 2y plus 3z, ln x plus 3z, ln x plus 2y, which means, okay, well, div or curl first. Let's do div. Partial derivative of this with respect to x. Partial derivative of this with respect to x, y. With respect to z, which means f is, who remembers the term? Incompressible. Curl. And I have much more difficult questions after this, so maybe one's off your exam. Maybe. And everyone's going to run back in now. Okay, so the curl of f, again. You may be tempted to memorize the vector form, but honestly, I think that you're better off just doing it by matrices and determinants. So this is partial x, partial y, partial z, ln 2y plus 3z. Oh, this is going to be not a very nice looking matrix. magic paper. Okay, so let's do this again. So what is the first component? Right, it is what we get when we do. See, what I really want to be able to do is point on this, but there doesn't seem to be a way. So if any of you are software developers, get on that. So we need to do this and minus that, right? So partial y of ln x plus 2y is what? Well, that's 1 over x plus 2y times 2 minus 1 over x plus 3z times 3. The next one is going to be 1 over 2y plus 3z times 3 minus 1 over x plus 2y times 1. The 1 is from taking the partial derivative of x with respect to x. Right? I'm just putting it in there to make chain rule really obvious. And the last one is 1 over x plus 3z times 1 minus 1 over x plus 2y times 2, which means that f is not conservative, right? Are we allowed to conclude that? No. So don't be tricked. That is that one. That one. Okay, and we'll finish out with this one, but it's kind of a doozy, so. This is 16.5, question 16. If f is conservative, find a scalar function f such that f is equal to delta f. Okay, first let's find the curl, right? Because if this isn't a conservative function, then we're doomed. Just setting it up here. 1. Oh, I didn't even define f. Sorry. F is 1 sine z y cos z. Okay, so we have 1 sine z y cos z, and the curl is going to be what? So the first one is going to be d dy by y cos z, which is what? Cos z. Minus d dz by sine z. Minus cos z. Next one is going to be d dx y cos z. Right, it's this and this. Zeros, yeah? And the final one is this. Also 0. So we're left with 0, which means conservative. Okay, which means that, okay, such an f exists. And so let's continue. To find f so that delta f is equal to 1 sine z y cos z, we know what? Well, we know 1 df by dx is equal to 1. Secondly, we know that df by dy is equal to sine z. And thirdly, we know that df by dz is equal to y cos z. Okay. what does this mean? Well, if 1 is true, this means that the integral of partial f partial x with respect to x is equal to the integral of 1 dx, which is equal to x plus a constant, which is what? A function of y and z. Of course, this is equal to f. Okay. So from 1, we've concluded f has this form. Okay. This means delta f by delta y is, well, the derivative of x with respect to y, which is 0, plus the derivative with respect of g, y, z with respect to delta z, partial z, which is equal to what? Well, by 2, this is equal to sine of z. Just yell out if I say something that is confusing. But does everyone follow so far? It's pretty standard. You're just iterating through this process. Because I miswrote. Thank you. And I'll type this up and put it in the notes. Okay, so where was I? Okay, this means that if I take the integral of the partial derivative of g, y, z with respect to y by y, we're going to get the integral of sine z dy, which means what? That g, y, z is equal to, what's the integral of this? Plus, plus a constant, but what constant? Well, it's going to be some function of what? Well, of z. It's true, but why is there no x in it? There is no x in it, but why is there no x in it? What are the variables that y, how did we define y to begin with? How did we find g to begin with? As a function of y and z. Therefore, it can't be equal to something with an x in it. Right? It would violate our assumption, right? So we can conclude absolutely that the constant here is going to be in z only. Okay, so we have this. I'll make this a star. And finally, star implies that f is equal to x. Right? F is equal to x plus gy of z, which is, oh, sorry, guys. That should be cos, right? Wait, did I? No. No. X plus y sine z plus hz, right? So this is where we're at now. We're almost there. This means that if we take the partial derivative of f with respect to z, we get what? Well, x with respect to z is 0. Y sine z with respect to z is y cos z plus the partial derivative of h with respect to z. And we know that this is equal to what? Y cos z. This means delta partial h by partial z has to be equal to what? 0. Which means that the integral of dh by dz by dz is equal to the integral of 0 dz, right? Which means what about h? Careful. What do you take the derivative of to get 0? Just the number. So h is just the number. No. Okay. We conclude f is equal to x plus y sine z plus k, where k some constant. And to follow my own instructions, let's just quickly check. Right? We have delta del f is equal to the, well, what's the derivative of f with respect to x? 1. What is it with respect to y? Sine z. What is it with respect to z? Y cos z. I'm just going to put a check mark here, right? Because if they go up, that was the original setup. So that's it. Sorry I couldn't give you more today, but this chapter was kind of easy. Do you like this? Should I continue this? I can do more after lecture type of questions. I'm not sure. Sorry, Echo. I didn't consider. Well, I don't know which screen's going to the Echo. Oh, okay. Well then, I redact my apologies. I won't put this online, but I'll type it up into the notes and send it out. No. I put the lectures on YouTube as well if you're looking for a faster way of accessing them, because the Echo's kind of shitty. So I uploaded them to YouTube for my own ego. Yeah, I don't know what the link is, though. I'll have to find it. Email me if you want the link to the, it's like unlisted videos on YouTube, but if you email me, I'll send you the link to where I've been uploading them to. Huh? They're already on Echo, though. I'm not sure that I'm actually allowed to do, oh, well. It's me, so if the university really wants to fight over if they own the words I speak and the slides I write, so be it. I'll take it down. But currently, I have them on unlisted videos on YouTube, right? Because I know you can't. There's no phone app for Echo, is there? No, so we're teaching you guys as if it's the 5th century. I asked for this like last semester, and I just got it now for the last 2 weeks of the course, right? Go bureaucracy. Anyways, return to your friends. Brave the weather. That's an exit? I had no idea that was there.